Hi there, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This video is for calculus students and it's an introduction to vectors video in which I introduce you to the concept of what a vector is. So first of all, just a quick definition. A vector is a quantity that has both magnitude and direction, whereas a quantity that only has magnitude is called a scalar. So here's two statements. Which one's a vector and which one's a scalar. So the first statement says a car travels 50 kilometers per hour. I clearly don't have a direction here, so that's a scalar. A car travels 50 kilometers per hour east. It has both magnitude and direction, so that's a vector. Here's another example. See if you can figure this out. One of these is a vector and one is a scalar. So obviously 30 centimeters is a magnitude, but it's not a direction, so that's just a scalar quantity. Whereas if I say 30 centimeters straight up, I'm giving you a direction as well as a magnitude. That's a vector. Now, before we do the next example, I just want to warn you, we're about to get into a little bit of science talk here. And that's because we want to look at the concept of force, which is something we haven't talked about yet in calculus, but we will. So if I wanted to move this particular object, I need to push it. And so what's happening is that I'm applying a force on the object. And force is something that comes up a lot when we talk about vectors. So how do we quantify force, or how do we measure force? So force is measured in a unit called newtons. Obviously it's named after Isaac Newton, that's why it's capital N. And the abbreviation for newtons is capital N. And so just so you know, 1 Newton is defined as the force required to cause a 1 kilogram weight to accelerate at a rate of 1 meter per second squared. So a bunch of scientists took a 1 kilogram weight, accelerated it to a rate of 1 meter per second squared, and said the force that took, that's called 1 Newton. So there you go, it's a metric measurement. Before metric, there used to be something called, I think, foot-pounds, or some very bizarre thing. I don't know, ask your closest American. Actually, you know, Americans use newtons, at least in the science world they do. And again, just to help you understand what a newton is, if you hold an apple in your hand, a typical apple about 100 grams, what you're feeling when you feel the weight of the apple in your hand is actually the force of gravity acting on your hand. And a 100-gram apple is being pulled to the ground by gravity, which is acting at about 10 meters per second squared, which is basically 1 Newton. So if you want to know what the force of a 1 Newton feels like, pick up a typical apple, and the weight of it in your hand is basically the force of 1 Newton due to gravity's pull. Anyway, you know, that's very sciencey. You don't need to know that for calculus. You do need to, however, know how to deal with newtons. So let's get back to math, our happy place. So here's two examples, and now I'm using newtons. That's why I wanted to make sure that everyone understood what a newton is, so we could now use newtons as a measurement. So we have one statement that says a child pulling with a force of 200 newtons, and another statement, a child pulling with a force of 200 newtons at 30 degrees to the direction of movement. So obviously the first one gives me a magnitude, like I know how strong the force is, but I don't know how this child's pulling. I don't have a direction, so that's a scalar. Whereas the second statement, I have both the magnitude, 200 newtons, and the direction. I know it's 30 degrees to the direction of movement, so that's a vector. So far, we've seen 3 different vectors, and each of these vectors has been described using words. But obviously there's other ways to represent vectors other than just describing it in a sentence or an expression. The most common way that we're going to talk about vectors is using what's called a geometric vector. So a geometric vector is basically literally a picture of a vector that we represent with an arrow. And so the arrow has, you know, there's the tail and the tip, so that there's clearly a start and an end. So we know that the direction of this vector, it's going to the right, like this. Oh, I just drew another arrow. But it's starting at the tail and going to the tip. So this is what a geometric vector looks like. And you can see that most of the time when we're working with geometric vectors, like in these two diagrams, so here's a vector, so you can see the tail and the tip, and we can see that this is a proper vector because I have both a magnitude, it represents 30 kilometers of displacement, and I have some reference to direction. I know that's 45 degrees away from true north. Here's another example. There's actually two vectors in this diagram. We can look at this one if we want. So again, we have a tail and a tip. We have a magnitude, it's 2300 newtons, and we know that the direction is 45 degrees from the other vector given. So that's how we represent geometric vectors, as with the diagram. We can also represent a vector using symbols. So for example, if I have a vector that goes from A, okay, that's not what I wanted to do. Obviously, I wanted an arrow. Here we go. If I have a vector from A to B, boom, then I can describe that vector sort of using math symbols like this. So this, AB with the arrow over top, means the vector that goes from a point called A to a point called B. So you'll get used to writing vectors like this. And you'll notice I sort of drew half the arrow. Quite often, for time and efficiency, we don't actually write the proper arrow. We tend to write sort of this shortcut arrow like that. They're both vectors. This is just handwritten notation. And we can also simply represent vectors like this, which is just saying there's a vector called V. Well, how do I know it's a vector? Oh, there's an arrow on top. So if I were to write this, that's not a vector. This is a vector, because there's a weird looking arrow on top. So here's an example. We're going to talk about a vector called V. Now, it's hard to see because of the program I'm using, but that's not a straight line. That's an arrow. Okay, so make sure that you have an arrow, not a straight line. So we have a vector called V, and it's got a tail at 0, 0 and a tip at 8, 4. And we want to determine both the magnitude and direction of it. So obviously the first thing I'm going to do is I'm going to pull out my Cartesian plane because the references are point references, and I'm going to plot both of those points. Can I get them? So let me plot those points. So we have one point, oops, at 0, 0, which is here. One point here at 0, 0, and another point if I go over 8 and up 4, there's the other point. So our vector looks like this. That's the vector to visualize it. It goes from here to here. Tail at 0, 0, tip at 8, 4. That's how I knew the arrow was pointing sort of up and out. So what is the magnitude and the direction? Well, the magnitude we can find pretty easily. Because it's on the Cartesian plane, I can see that there's a right angle triangle happening. So we can just sort of use our Pythagorean theorem and say that the magnitude of vector V would be the square root of 8 squared plus 4 squared. So 64 plus 16 is the square root of 80. We could write that perfectly if we wanted to, but we could also, I don't have my proper calculator here. That's not good. Come on, Townsend. Where's your calculator? Okay, so that's 4 root 5. Okay. So that's the magnitude of vector V. And even though I'm going to explain this more carefully later on, this is how you actually write the magnitude of a vector. These are basically absolute value signs because absolute value, when we say that, like when you say the absolute value of -6 is 6, what you're really doing is you're removing the direction from it. You're not, if you think about a number line as having a positive direction and a negative direction, -6 means go 6 to the left of 0, and the absolute value of -6 means 6 units away without a direction. So that we use absolute value signs to represent the magnitude of the direction. Now, of the vector, sorry. So to find the direction of it, I'm going to use an angle, and I'm going to talk about an angle here. So if I use tan theta would be 4 over 8. So tan theta is 1 over 2. And now I'm really wishing I had my calculator handy. Oh, I do. You're getting the unedited video. And yeah, we're in degree mode here, guys. Deal with it. So, well, I guess we could describe it not in degrees, but this unit generally we're going to use degrees again. So that is about 26.6 degrees. So how would I describe that as a direction? I would say that vector v is 26.6 degrees above the x-axis. And I might clarify more in the positive y quadrant. That's certainly more than I need. And again, later in this video, I'll talk about how else you could have described that direction. So there's the magnitude and direction of a vector. Oh, and good. Here's where I talk about it. We use absolute value signs to indicate the magnitude of a vector. So that basically takes a vector and says, ignore the direction, just how big is it? So it turns a vector in a way into a scalar. So for example, if I want to find the magnitude of vector v, I don't care about an angle anymore. All I care about is just how long is that line relative to 8 centimeters and 14 centimeters. So again, obviously, we're going to use Pythagorean theorem. So on. I could just find the magnitude like this. Calculator. Ooh. So it's root 260, and of course I might reduce that or turn that into a decimal, but I'll leave you to do that. So again, this time I didn't ask you for the angle. If I'd asked you to find v, then you would have had to both do this and find an angle. But for now, that's not what it actually said. So let's talk about how to describe the direction of a vector. There's a couple different ways you can describe the direction, one of which we've seen already, which is where you describe it as an angle reference from something else in the diagram. So 30 degrees from the horizontal would look like this, but it could also look like this. So it can be a little ambiguous, and sometimes it depends on the situation. Here, I could describe this vector as being 45 degrees away from the other vector. However, you can also describe it using sort of north, south, east, and west, and there's a couple ways of doing that. One is called true bearing, which is really fancily called azimuth bearing. This is actually what pilots use when they talk about the heading of an aircraft. Basically, you treat north as being 0 degrees, and then you rotate clockwise, and wherever you are, you measure the angle from 0 degrees. So that means if I'm literally flying like this, really close to north, I'm flying at a bearing of like 350 degrees or something, because I'm clockwise really far away. So so in this example, so in an example might be that an aircraft is flying on a bearing of 127 degrees, and that means that from true north, you measure clockwise 127 degrees, and now I know that the plane is actually flying in this direction. Okay, so that's azimuth or true bearing. But we're more commonly going to use something called cardinal direction, which is also called quadrant bearing. I generally just say direction in this case. And again, it's also based on north, south, east, west, but you can see it looks different. Here's an example of what it looks like. This is north 28 degrees west. And there's 3 pieces here, each of which has to exist in the cardinal direction. So the first thing that you have to have is you have to have a direction here, which has to be north or south. You never start east or west. You always start with north or south. Then you have an angle, and then you have either east or west here. So for example, this one says north 28 degrees west. Now what does that mean? There's an international way of understanding that, and we all have to understand it. So what it means is that the direction that this vector is heading is 28 degrees away from north in the west direction. So again, let me, that probably doesn't clear it up too much, so let me sort of draw you a little picture here. You're going to get used to drawing these little pictures, trust me. So if we think about, oops, let me draw a nice picture for a second. So if we think about north, south, east, and west, if I have the bearing again, oops, north, 28 degrees west, here's how you interpret that. So we're definitely heading north, not south, right? So we're heading somehow up in this setting. And I'm heading 28 degrees away from north. So 28 degrees this way or this way. Oh, towards west. So I'm heading roughly northwest. And I can tell you that I'm heading, in fact, exactly 28 degrees away from north in the west direction. That's how you read these cardinal directions. So I'm just going to give you another example because this is really, really important to a lot of the work we have to do that this stuff is comfortable. So if I said south 10 degrees west, what would that mean? Or what would that look like? So obviously, again, here's north, south, east, and west. I know that I'm basically heading, okay, I'm basically heading south, not north. And I'm heading 10 degrees away from south in the direction of west. So here's south, but I'm not going due south. I'm going 10 degrees away from south towards the west direction. So this line here represents the direction I'm heading on the cardinal compass. Okay? So let's put both of those new things let's practice them. Here's, I've drawn this blue vector arrow, and I want you to describe the actual direction using both azimuth bearing and cardinal direction. So, feel free to pause if you want to do it before me. So in the azimuth sense, or true bearing, we need to consider that north is 0 degrees, and then we have to swing all the way around to where that vector is and describe completely what angle we had to go through to get here. So obviously I'm going 90 plus this bit, and that bit must be 20 because that's 70 and 20 is 90. So 90 plus 20 is exactly 200. So this is a bearing of 200 degrees. And you'll notice with the azimuth or true bearing, you never write a north or a south. You don't put any of the actual directions in it because it's understood what it means. That it's measured from north in a clockwise setting. Now in terms of cardinal direction, I know that in general this is more south than it is north. And I know that it's more west than it is east. And so what we need to do is we need to say, so if I was going due south, I would just say south, but I'm not. I had to move a little bit towards the west. So how much did I move towards the west? I moved 20 degrees towards the west. So that is south 20 degrees west. So I hope that's helpful. And then just some important additional terms related to vectors. Equivalent vectors. So if we talk about equivalent vectors, we mean vectors that have both the same direction and the same magnitude. So if you look at this parallelogram here, and instead of thinking the side, don't think of the sides for a second as line segments. Instead, think of them as vectors. So there's a vector here called PQ. And what would be a vector equivalent to PQ? This one, RB. Those are equivalent. They're the same magnitude and they're the same direction because, again, I called it a parallelogram. There's another vector, obviously here, vector RP, and that's equivalent to BQ. And I could have reversed that. I could have said, that vector PR is equivalent to vector QB. So, where are they? There we go. So there's actually a couple different things. PQ and RB, I started with that, but I could have said QP and BR. Similarly, RP and BQ, or PR, and QB. Those are all equivalents. You can also talk about what are called opposite vectors. Opposite vectors have the same magnitude, but the exact opposite direction. So in other words, if I talk about this vector from P to Q, the opposite vector is this vector from B to R, because they're the exact same magnitude, same length, and they go exactly opposite each other. And if you're worried about what that means, it means basically think about 180 degrees, exactly opposite. And so if you look at this diagram, you can see that there's a bunch of different opposites. But if we say that they're opposite, then we can write this. We can write that P to Q is the negative of QP, and that tells me that it's opposite. So I'm saying that this vector is opposite this vector, which is pretty obvious. Also, it's opposite this one. Yeah, so it's also true that PQ is opposite BR. So I just want to tie together the idea of equivalency and opposites. If it's true that vector AB is equivalent to CD, then it must also be true that AB is opposite DC. So from the visual, I think that's obvious, but it's also important, not that we spend too much time on what's called vector proof, but even without the diagram, I would know this to be true, because if I was given this fact, that AB vector is equal to CD vector, then I can simply reverse the letters on this and get an opposite vector. So CD must be opposite to DC, because I just went the other way around, basically. One more important term is parallel vectors. Parallel vectors have either the same or opposite directions, and they don't have to have the same magnitude. So think of it as like parallel lines, basically. They're parallel, meaning that they go in the same direction, or maybe the exact opposite direction, and we don't care about the magnitude if we call them parallel. So if I look at this little diagram, I can see that vector ED is parallel to FC. Or I could say that ED is parallel to CF. And how do we write parallel? So parallel, if I say ED is parallel to, these two lines here mean parallel. It's the symbol for parallel. And if you're writing it on paper, like most of the time you will be, you write it nice and big. It should absolutely positively not look like the number 11. It should look like parallel train tracks, because that's really what it represents. Okay, so that's your introduction to vectors. And I'm leaving this picture here because you might know who this is. And if you don't know who it is, that's your bonus question. Figure out who this is and why this guy's picture is in this lesson. Hope that was helpful. Bye.